Hello, linear algebra students. Let us begin Module 14, Eigenvectors and Eigenvalues. A preparation first. Let V be a vector space. Then, a linear map L from V to itself is called a linear operator. Now, if this linear map goes from V to, say, another vector space W, then we do not call it a linear operator. For example, if it is R3 to R5, then no. Linear map from V to itself is called a linear operator. For example, we have to have a square matrix. In this case, we define a linear map from R3 to R3. Alright, so much for the preparation, and let's go to the definition. Let V be a vector space, and let L be a linear operator in V. Alright, a non-zero vector, small v, is called an eigenvector if there is a scalar lambda such that L of V is equal to lambda times V. In short, in V direction, the linear map L is a expansion or contraction, depending upon the size of lambda. Lambda is greater than 1, then expansion toward that direction. Lambda is less than 1, in absolute value, then it's contraction. Less than 0, then in that case, it's going to the opposite direction. In English, an eigenvector is called a characteristic vector, but for historical reason, we use the German term eigenvector more often. Here, the scalar lambda is called an eigenvalue. In English, it is called characteristic value. One thing to remember, eigenvalues can be 0. This can be 0. In that case, you have to find out a certain v, which is non-zero, yet L of v is equal to 0 times v. But eigenvector is never a zero vector. We have to have a non-zero vector here. Okay, so much for the definition, and let's go to some example problems. Here's the first type. We have a linear operator given by the square matrix. Yes, we need a square matrix because we have to go from Rn back to Rn, same dimension. Show that the vector 1, -1, 1 is an eigenvector with the eigenvalue of lambda equals to 2. Basically, I have to prove this. A times v is equal to 2 times v if v is 1, -1, 1. That's what we have to prove. In other words, okay, that's what we have to prove. So let's write it like this. In other words, this matrix times 1, 1, -1, 1, -1, 1 should be equal to 2 times 1, -1, 1. This is what we have to establish here. See this? L of v is equal to lambda times v. L of v is equal to lambda times v. Is it true? Let's check. It's not a difficult problem. Just do your computation. A of v, just matrix multiplication. First row times column, we have this dot product here. Next, second row, this column, we have the second dot product here, and so on and so forth. If you do it right, you're going to get 2, -2, 2. And that is twice of 1, -1, 1. So yes, the answer is yes. How about the next problem here? Show that 1 plus square root of 6 is also an eigenvalue of the same matrix. Same for 1 minus square root of 6. And find the associated eigenvectors. Okay, I see. These are harder. Not just more difficult in terms of more complicated eigenvalues here. We have some square root flying around. But also, I did not give you the eigenvector. Maybe I'd better come back to this. Let's change this a little bit. Show that lambda equals to 2 is an eigenvalue. Also, find out associated eigenvector. Okay, all right. So, let me change the first problem into this. Instead of giving you 1 comma negative 1 comma 1, I gave you only lambda equals to 2. And I'm asking you to find out the eigenvector, and it should turn out to be 1 comma negative 1 comma 1 if you do it right. Let's see. So this problem is a little bit different. So AV is equals to 2V That's basically what you want, right? Lambda is given as 2. Okay, in other words, and this one I don't know, so let's take xyz. Equals to 2, and then this matrix xyz. Okay, here's a problem. All you have to do is to find out this x comma y comma z, and you're through. So here we go. AV equals to 2v because lambda is equal to 2. So that's this equation. First equation here. I can highlight very well. And then we have to find out the solution for the second. All right, how do I do that? Well, let's do the computation. The left-hand side becomes like this. So 1, 2, 3 times x, y, z. So 1x plus 2y plus 3z is equals to this. (2x), but nobody writes it as 1x. Just x is fine. And then this one is 0x plus 1y minus 1z is equal to 2y, but nobody writes like this. It's just y minus z. And then third row, 3x plus 3y plus 2z is equal to 2z, and here I'm looking for x, y, z. Okay, let's work it out. Which is the simplest? Looks like the second line is the simplest to me. So let's begin with the second line. So y minus z is equal to y. So negative c is equal to just y. Therefore, y is equal to negative z. Okay, how about this? Does it make sense? Okay, let's put it into the first line. X plus 2y plus 3z is equal to 2x. But then again here, y is equal to negative z. Therefore, I get x plus z is equal to 2x. Did I do this right? Therefore, 2x, excuse me. Therefore, z equals to x. How about this? Does it look okay to you? Okay, how about the third line? Let's go ahead and check. Put everything here. 3x plus 3y plus 2z equals to 2z. And then x is equal to z. And y is equals to negative z. And then if you solve everything, what do you get? 3z minus 3z cancel out. 2z equal to 2z. Oh, that's okay. So this is always correct. Therefore, we get this. Z, negative z, z. So here goes an eigenvector. As long as this is non-zero, it's okay. But I can make it simpler. What's the simplest non-zero number here? Putting in z equals to 1, we get x, y, z is equal to 1 comma, negative 1 comma 1. And that's precisely what we wanted all along, isn't it? Somehow, if you did not like 1 comma, negative 1 comma 1, I could have selected something else. Instead of 1, I could have selected, say, negative 1. In that case, this will be negative 1, 1 comma, negative 1. Or I could have selected 10. I'm going to get 10, negative 10, 10, kind of like that. There are infinitely many possibilities here. But why would anybody bother selecting more complicated number if you can select z equals 1? So there goes an eigenvector here. Just remember, don't select 0. If you get 0, then you get 0, 0, 0, and that's not an eigenvector. You cannot have 0 vector there. The definition of the eigenvector included non-zero vector. Where is it? We have to have non-zero vector. Otherwise, okay. So usually the easiest is 1. So see the difference. If you already have 1 comma, negative 1 comma 1, just direct computation, easy. If you don't, then you need some further computation. How about a little bit harder problem? 1 plus square root of 6. In that case, same deal. AV equals to lambda v, or in this case mu v, because I already used up lambda. So 1 plus square root of 6 times x, y, z. So we have these three equations, blue, red, green, like before. And then just like before, the second equation, red is the easiest, so let's work it out. Y minus z is equal to y plus square root of 6y after breaking up and canceling something, and in the end I get z equals to negative square root of 6y. Okay, previously I solved y with respect to z, but this time I decided to solve z with respect to y. That's fine. And then I'm going to plug in y equals to some simple number, preferably 1. Alright, now let's go to the first line here and break up the parentheses we get first. And then before plugging in, let's do some simplification. This x and that x cancel out, and we get the second equation. And then just plug in z equals negative square root of 6y. So here, instead of the z, we have negative of square root of 6y. So we got this negative and then that. And right answer is square root of 6x, and you can solve for x. If you do it right, you get square root of 6 over 3 minus 3 times y. Plug all these into the third equation, and then do you have something like 1 equals to 1 or z equals to z, something trivial, or you could have reproduced all these all over again, as I did here, and check if you get the same thing. That means we are in business. I can use either blue or green because they're the same. So plugging in y equals to 1, we have this vector. I already used up, so let's call it w. W of x comma y comma z, and x is square root of 6 over 3 minus 3. And then y equals to 1, so 1, and then negative square root of 6. Here, plugging in y equals 1, plugging in y equals 1, or here, plugging in y equals 1. By the way, what if you don't want to plug in y equals 1? If you plug in y equals to 3, multiply by 3, and why am I doing that? To kill off this denominator, then that's going to be killed, and I'm going to get 9, and that will be 3, and multiply by 3. So I'm going to get something like this. A little bit more space here. And that looks a little bit ugly with this another parenthesis here. Okay, that looks a little bit better. And then I already used up w, so let me use something else. Oh, wait a minute. This hat may give you an illusion this is a unit vector. It's not a unit vector, so let's choose something different. Oh, whatever. You don't have to select y equals to 1. Traditionally, plugging in 1 is a good idea because that's the second simplest number after 0, and you cannot plug in 0. But in some case, like this, when you want to remove the denominator, you're selecting some different number like this. You can do that. As for y equals to this one, as for the other eigenvalue, nu equals 1 minus square root of 6, I didn't do it. I'm going to leave that to the students. Now, do we have enough time for some abstract problems? Abstract, therefore easier. Okay, let's consider the derivative operator in the space of all differentiable functions. And then, what is the eigenvalue of lambda? If you know the answer, it's really simple. It turns out this function, f of t is e to the lambda t. If you take the derivative, exponentials stay the same. But by the chain rule, we have to multiply the derivative of the inside. And that's how we get this lambda. So what do you get? Derivative of f is lambda times f for this particular function, e to the lambda t. This conclusion is going to be very, very useful in differential equations. How about the next example? We have a diagonal matrix. All right. Identify all eigenvalues. It'll turn out we only need the diagonal entries. Just plug in the standard unit vectors e1, e2, e3, 4, and so on and so forth, 1 and all 0, and then 0, 1 and all 0, etc. And you're going to get lambda 1, lambda 2, lambda 3, and so on. Now the question, is there any more? I mean, we have this n eigenvalues, lambda 1 through lambda n. Could be some duplicate. Some of them may be 0, but we found them all. But is there any more? The answer is no. We can have only the diagonal entries, nothing else. But that proof is a little bit difficult, and we're not going to prove it here. Just remember the conclusion. If you have a diagonal matrix, then just the diagonal entries.